Sure. Hello, everyone. Hi, I'm Chaitra Ravada. I work as a machine learning engineer at Twitter. And over to you,
Hi
John.
everyone. Hi everyone. I'm Joinal Ahmed. I work as an AI projects lead at Google Cloud. I talk about mostly about ML advocacy, trying to evangelize new things. So that's about me. So we'll quickly jump into the session. Tom, please.
Hello, everyone. Thank you for joining. I'm Chaitra Ravada, and I have my co-presenter Joinal Ahmed here, and we are here to walk you guys through how to take data to next level with graph machine learning. Now let's zoom out and see how large-scale connected data has led to digital megatrends like data-driven discovery and innovation, hyper-personalization, or AI and ML in AI and ML. And I'm pretty sure all of us here would have experienced at least one of the applications, like product recommendations or personalized healthcare or price optimization and etc. Now let's see how these different arrays of data are stored and consumed. We have one-to-many relationship, like a customer buying multiple items in an order, many-to-many relationships, like how different products are bought together when you look at from an organization standpoint, or hierarchical data like product details, like where you have a department, underneath that you have category, and within that you have subcategories and etc. Now, all of these data points are typically stored in our legacy SQL systems. Like consider your transactional data where we store every order and their order details in one individual row. And then we use data lakes to transform these transactional data by joining with customer data or with product data, etc., to build columnar relationships with across different data points. However, there's a hidden data where we can also leverage into different rows, the relationship between different rows. And why do you think that is important? Consider social media platforms or big e-commerce companies like Amazon or enterprise companies like Google, right? They all have these networks where they know what a customer had bought, what they have viewing it, or what they've bought previously, what they're interested in, and etc. Like if you look at this example, right, you can actually know that a customer lives in a particular country, likes football, and is a fan of a particular FC club, right? And the probability that if you recommend them for a match in a match where where the football club plays, the customer is likely to go. Or if you recommend them a jersey of that football club, then the person is likely to buy. So you're actually enabling customers to make informed decisions by leveraging this cluster of knowledge. Now, our traditional DBs don't handle these relationships well. Like though earlier, like I've said, right, we do have we could join to get those columnar relationships. At the same time, we could do joins for individual rows and get row-wise relationships. But then, as the level of relationships increase, the more and more relationships you want to join, your join complexity kind of increases, and that leads to your performance. That affects your performance, which leads to which becomes really hard to maintain and very difficult to scale it to. And it especially becomes a bottleneck when you want to do all these iterations in real time. Now let's see from NoSQL databases. Like we do have key value pairs DB like Redis, or columnar DB like Cassandra, or document DB like MongoDB. Over here, you can store your data in an unstructured data like in JSON or in different formats you would require. You like, but then you still are not able to have the row to row relationship, which we mentioned earlier. And that's where graph DB kind of comes in. And Neo4j actually enables you to have the relationship between two different rows. So now let's read or look into more about the anatomy of the graph, right? So every graph has nodes, and every node has properties where we store the data in a name value pairs. Like in this case, we have persons with property called name, the date of birth, or geography, or when they have joined a particular platform, and etc. And now two different nodes are joined by edges, which are called relationships. There's unidirectional relationship or bidirectional relationship. Now let's see how our Neo4j actually fits with suite of Google Cloud databases. For document uh, for document data, we have Firestore. For key value data, we have Cloud Big Table. Similar for Graph DB, we have Neo4j. So this is how we can use different DBs within Google Cloud. And the advantage of Neo4j is it can be used by everyone who consumes data. Like we can query the data in human readable format. It also has built-in algorithms like PageRank or GraphStage, where you can actually get the values out of it. Sorry, we can it actually yeah, PageRank or GraphStage and other algorithms where you can get embeddings which are kind of needed in this scenario, right? Consider we have a lot of categorical data have a lot of high cardinality, which results in very sparse data, and that's when embeddings kind of help in using those sparse data and convert to embeddings so that we can use those embeddings as features, and we can model our ML model from there on. Now let's see how Neo4j can be used in Google Cloud as an end-to-end ML architecture. We have cloud storage where we get data, or we have BigQuery where we fetch data and we transform it in the data flow pipeline. And from there, we can pass it to Neo4j GraphDB, where it converts your structured data into graph data. Or in case if we have live stream of data, we can actually pass through Apache Spark and get real-time graph built on top of that data. And now we would pass it to either Neo4j Graph Data Science, where we can use the built-in algorithms, or we can also build custom algorithms on Vertex AI. And similarly, we can also use Neo4j Bloom to actually build business intelligence reports and put it up on Looker dashboard, and visualize it on Looker dashboard. We can consume both of this data if we want in real time, or we can host it and we can get live stream of data on Kafka as a service. That's mostly about my time. I really hope you were able to understand how Neo4j, why graphs are important, why GraphDB is important, how Neo4j can actually help in end-to-end ML model. Now, I would like to pass on to Joinal for him to walk you guys through a demo where we use Neo4j with Vertex AI. Thank you.
Thank you for going over all the graph TV concepts. Now what we'll do is I'll go over a very simple use case, a very simple example project on fraud detection using the facing synthetic dataset, and we'll use Neo4j for building the graph embeddings, creating the graphicality between these different attributes, and then we'll create embeddings out of it. And we'll then use Vertex AI for training the model, exposing them into an endpoint, and we'll start making interpretation. The whole notebook is available on Google's GitHub, so you can actually go and uh, try this example yourself. I think that would be more helpful for people to get a hands-on understanding of how it works. And also the whole thing is covered in a Google blog, so if you want to go ahead and read, feel free. Going ahead, so this is how the project or the use case is planned out. So we have this different data, that aggregated transactions, the client profiles, overdraft limits, initial balance distributions, and others. We'll collate everything together and create a graph out of it. Now, once we have that graph, we'll leverage those embeddings to train a model with Vertex AI and then expose them as an endpoint. It's demo time now, so I'll just quickly go over the notebook that I have. I might not go in a very detail on a line of code basis, but I'll give you an over understanding of what is happening, and then you can go ahead and try it yourself on your own So here to start with, I connect to that graph DB, and on that just I'm just exploring the data, doing some simple EDS steps. So here I'm just trying to explore what are the kind of labels I have on my data set, and for that I run this simple graph DB Neo4j query called db dot labels and yield labels. So I'm extracting all of the labels, matching this criteria, and I'm just counting how many of these happens here. Right? So I can see uh, the labels like cash in, cash out, payment, the transactions. These are our top labels in our data. Similar thing, I just explore what are the kind of relationships that we have on the data. Again, just a very similar query to extract all of the data, all the relationships that we have on our data, and it shows perform to next. These are some of the top relationship that we have on our data. Next, I'll just want to explore the transaction type. Again, very similar. So I'm matching the T transactions and summing the amount, global sum count, matching this criteria and exporting them into our table, right? Exporting them into a data frame so that we can explore them further. Now that we have this graph, we know a bit about the data itself. Let us now create new features with the graph embeddings. So for that, I am again running this relationship query. So client perform transaction to another client, and I'm extracting all of this data out and the embeddings that were there, along with the number of transactions, total transaction amount is fraudster, right? If that transaction or if the client is a fraudster or not. So I'm exporting everything into a data frame, and this shows that this query ran on about 11,000 nodes, and it and 26,000 relationship counts. Now, once I have this data, I can mutate it even further uh, to so that this fast RPA, right, which is a very more featured and high performance node to vec algorithm. So I can then convert these nodes into vectors and then start leverage them for my model. Now once I have these data, right, the embedding, the label, right, if it is a fraudster or not, the number of transactions which happened, and the total number of total transaction amount that was involved. For the simplicity, for the sake of simplicity, what I'm going to do is I'm going to dump these data as a CSV files into cloud storage, and from there I'll read this data for training the models. So once I dump this data here into these cloud storage paths, I can then create a AI platform on Vertex AI tabular dataset. I pass on the cloud storage location that I have and give it a name. Now, once the dataset is created, I again create an AutoML tabular training job and pass on the data that I have and which target to predict on that data split and other metadata which is specific to this kind of model, and tell it if it is a classification model and other details, right? Now, once I do that, this is going to start a model training job, and we can quickly see this model training job here, right? For example, if you quickly go through this link, we can see that like all the metadata which is attached to this model, how it performed, how much accuracy it gained. We can also look at the column metadata, what are the kind of data that we had, instances of each of the data. We can also explore them. And now going back, now that our model is trained, we can then expose this model as an endpoint using model.deploy construct and just pass on the machine type that is required for it. Once that is done, we can now start consuming this model from that endpoint to make predictions. For that, reading that huge CSV file from that cloud storage might be difficult. So, which is where we leverage GCP Vertex AI feature store. So all my data which was in these CSV files, I just repopulate them into a feature store. So from there I can start consuming them into my endpoint to make the predictions. Uh, yeah. So once I do that, so this is an example API call construct, which I have used here. If you just look at, this is the feature that I'm creating for my example call. So I have this number of transactions. I just wrote it 80. Total amount is this, and the saved embeddings that I already have. I appended it all, and this is how this instance of data looks like. Now I can call my endpoint with endpoint.predict and pass on this payload for it to predict. And what it does is it predicts that with 88% confidence that this instance or this user is a fraudster, and the model is pretty confident, right? So now from here, that you can pass on any data from your real-time environment to predict and then take downstream decisions on top of that. That's all that I had. There are just two more pieces of code snippet which will help you to clean up your Neo4j and Google Cloud environment. Going back, if you want to learn more, you can go to these links, neo4j.com /Google. So you'll get to understand the Neo4j and Google Cloud ecosystem and how they fit in even better. If you want to go ahead and do some certifications, have a hands-on understanding of the things, go to neo4j.com /graphicademy, and you'll be able to do some of these GDS and GraphDB certifications, and these are very helpful certifications for you to understand it in a bit more detail, have a hands-on understanding. For the purpose of this use case, you can go ahead in our Git repo and find the notebook available there and start using it. Thank you. Thank you, everyone.
Thank you, guys. Thanks for that presentation. It was great. I think I can see we had a question come up, so we've got a bit of time to spare, so I'll definitely post this to you. We had Alexander Nicholas had a good one here. If I can show this on screen, he said, from his experience doing machine learning, it is required to pre-process the data before doing any data training and testing and evaluation using the models. How accessible is the graph data on Python, and can we process it as simple as using a CSV or XLSX dataset? Any thoughts?
Yes, right. So it is very simple, right? So let's say if you want to, once you have populated your graph data in a new project database, so you can quickly run your most of the common algorithms right there using the simple, graph dot cipher construct. But if you want to do it go ahead in a bit more detail, let's in this example how we extracted those embeddings, and then those embeddings we stored them in CSV. So for each node you have them embedding, and then you leverage them to now train a tabular model or any sort of other models. Right. The other use case could be you could take a snapshot of the graph itself, and it's very simple, right? You can use these Python the packages that helps you to create those graphs. So you can embed in use those to create those graphs, and then run GCS model on top of that.
Excellent. Thanks for that. I can see as well that there are many people who are interested in getting their hands on some of the resources throughout the presentation that you linked at the end. I understand we're going to be making the presentations available after the event, and we'll certainly get everyone notified when the recordings are uploaded and ready to go. So we'll definitely get those out to everybody. Is there any more questions in the chat? I think, oh, here we go. We've got one from Garima Goyal. Does adding huge embeddings data slow the performance of Neo4j with respect to real-time BI requirements? So that's something that you run into. You could shed some light on, guys.
I'll take this question. So it shouldn't really impact the performance as much as you would expect, right? Like with complicated joints and stuff. So and also by huge embeddings, it also depends on the layers of embeddings you want to have, right? The number of neurons you want to have. So short answer, it wouldn't really affect much. Yeah.
Fantastic. Thanks, guys. Oh, we've got another question here from Timothy Huey. There's a question about the schema. Should transactions be nodes or relationships?
Thanks,
I've
guys.
seen some company put transactions as nodes.
Uh, so the transactions can be the relationships, but the product or let's say the person right who did the transaction. Let's say if I do a transaction with Chaitra, right? So we are the nodes, and the nature of transaction is the relationship between us.
And you could also have like product details in the node itself, like node properties. Yeah.
Yeah.
Thanks, guys, and thank you, Timothy. Ah, nice, Joinal. I can see that he's put some links into the chat as well. So anyone who wanted to get their hands on those, please have a look at what Joinal's just linked. And that should be good. I think if there's no more questions, feel free to keep them in the chat, guys, because we still have some time. But if that's it, then we're happy to go to a little bit of a break, perhaps.
Sure. Thank you, everyone.
All good,
Thank you,
all good.
everyone.
Thank you, Tom.
Thank you, Joinal. Thank you, Chaitra. Have a fantastic day, and we'll see you around.
Sure.
Oh, actually, before you go, we've got a question snuck in there. That's all right. I've got one from Amber. Amber Lou, how many relations can one node have? Is there any limitation? Joinal, that one might have
Uh,
to go to you.
so it is limitless virtually, right? So it depends on the kind of instance that you are running that DB on top of the kind of memory it has. The graph doesn't has a limit. It's just that you'll hit the infrastructure limit when you try to operate those. You might have to upgrade your underlying infrastructure if you anticipate that your graph will grow over time.
Excellent. I can see Rohit has chimed in as well in the chat. No, there is no limitation. Thanks, Rohit. No worries, guys. If you want to jump off, we'll have a little break until the next talk kicks off in 10 minutes or so.
Sure, sure. And like if anyone has any follow-up questions, maybe we are on LinkedIn, so reach out to us there, and we'll be happy to answer any more questions.
Excellent. Thanks, guys. Appreciate it.
Thank you.
Thank you.